Good morning and welcome to the Dynasty webinars. My name is Bloem and today is the first presentation of a series of 6 that will be given during each Wednesday in September. This morning there will be my presentation and it will be followed by the presentation of Paul Baker at 11 o'clock. And we have to thank already our webinar management team, Maria Kapsalaki and Valerie Leprince. They will be of our assistance during the morning. Before I start, there is some information. If you can't hear the webinar, look to the instructions here to switch on your audio or video speaker and microphone setting. In order to make communication with you possible, we ask you if you can make your questions during the webinar presented, locate the Q&A box and write your question there and send it to our management team. Please do not use the chat box. If there is no time enough to answer your questions, note that you can always send it to myself, Hans Bloem, at INIVE.org. But note also that all remaining questions that cannot be answered today, we will have an opportunity at the last webinar, the 30th of September, to answer to your particular questions. Also, it is important to note that the webinar will be recorded and it will be published on our website, dynasty.info, within a couple of weeks, and often it is already within a couple of days. So, starting with the first presentation in this series of 6, it will deal with an introduction to Dynasty analysis techniques for building energy performance assessment. Dynasty is an informal network and it exists under the umbrella of the INIVE EIG, the Economic Interest Grouping. For details about the whole organization, I refer to the webinar of last week, and that can be found also on our website, dynasty.info. The strength of the Dynasty network is in its multidisciplinary expertise from over 25 years. The network is composed of participants from all over Europe, universities, research laboratories, and industry. The presentations, therefore, are made by 6 different lecturers. This series of 6 presentations cover the following topics with a focus on dynamic analysis methods applied to experimental data for the assessment of building energy performance characteristic data of building components, building elements, or whole buildings. So we deal with building physics to support the development of mathematical models for the energy performance assessment. Some basic knowledge of thermodynamic processes like the heat transfer and the impact of solar radiation is required. And that means knowledge on thermal conduction, convection, and radiation, as well as the thermal mass. In the presentations, the complexity of the physical process and how to translate the available information in mathematical models will be discussed. Importance of model simplification of building physics is represented by measured signals. The variability of the environments and the uncertainty of data that may result from measured data and not measured phenomena. We will focus on how to build a mathematical model based on the available input. For training, we are using benchmark data series, as you will see later. The objective of Dynasty as the network is to be a global leading network on dynamic testing and evaluation of energy performance in the built environment. Our aim is to consolidate our more than 25 years existing knowledge. Dynasty organizes regularly workshops, symposia, training that cover all aspects dealing with energy performance of buildings. Presently, Dynasty is task leader of task 5 of the IEA EBC Annex 71, dealing with building energy performance assessment based on in situ measurements. Before going into detail, I have to mention some aspects related to this presentation. Some brief explanation about dynamic, experimental testing, and the energy performance of buildings. Dynamic processes involve the aspect of time. To analyze dynamic processes, dynamic mathematical techniques are required to extract dynamic information from experimental observations. In the built environment, dynamic behavior is importantly present due to the thermal mass of the object, whereas outdoor environmental conditions are variable. The dynamic behavior can be assessed up to 4 time constants. It can be at yearly level, seasonally, daily, hourly, or even shorter. Often only 2 time constants are considered. So appropriate testing should provide the requested information, means the measured data. As you can see, as an example in the next slide, the data that you see here presents minutely data of an in situ measurement of 3 consecutive days. The technology nowadays makes collection and analysis feasible of a huge amount of observations. I will come back to that point later. And what you are seeing here in this graph are the resulting temperatures from solar radiation on an object. Concerning the energy performance of buildings, according to the EU directive, it deals with calculated or measured values, and in particular for heating, cooling, ventilation, hot water, and lighting. Over the recent years, interest is growing for a third approach, which is an holistic approach, and that is using administrative data. It is straightforward, it is less expensive, and it might, in certain circumstances, help the aim of the energy performance of buildings directly. Note that the harmonized calculation rules are presented in CEN ISO standards. Concerning measurements, a very limited number of standards are available. To make the relation between energy consumption, energy efficiency, and energy performance in building more clear, we have drawn up this figure to recognize 3 squares that represent these 3 aspects. So in the light blue, you see the energy depending on the building fabric. So material. It depends also on the climate zone where this building is situated, but also on the minimum requirements that each member state may have set for that circumstances. In addition, building systems, energy systems are needed to provide the conditions that are required in the building. And of course, it depends a lot on the available energy mix. And the nuclear power can be everything that is producing the energy that is needed. These 2 squares together, they form, importantly, the energy performance that is required by the directive. And the indicator gives a value that is representing that. If we are looking a little bit further to the big blue square, then we see also that another energy consumption is important, and that is depending on the occupants, the behavior of the users the appliances that can be found in the building, and of course its functionality. An hospital or a school, they are quite different from the building that we are living in. Often we can get that kind of information from the metering data. Metering data includes the energy used by the consumption of the users as well as the fabric in its climate. In the future, we will look more into detail in the relation calculation and metering data. Over the years, it appeared that the calculation of the energy performance and the result from measurements did not match or varied a lot. The discussion started how the gap could be explained, and it resulted in experimental research in several countries. European and IEA projects were starting to focus on trying to understand the gap. Are the standardized calculation rules, or are the measurement methods inadequate? I've put there some of the technical committees of CEN that are dealing with all the aspects of energy performance of buildings. A close look to energy performance assessment is why is it required? In order to reduce energy consumption, reach savings, we like to save energy, one needs to know what is the current consumption. So it is also a justification for investment of renovation of buildings. Important aspect is also to improve the energy efficiency of appliances and energy systems. And it might be also leading to the change of fuel. The overall energy performance assessment of the building should include nowadays also renewable energy, the application of the techniques or the integration in the whole energy system. And it is clear that characteristics are becoming more prominent, like we can find in the time constants, and as a result of the use of appliances, the gains of the appliances, solar gain, but also the behavior of the occupant. Also, the aim is to have new buildings at the level of net zero energy buildings. The EPBD requires already now a monthly calculation, and in some cases an hourly calculation. Important issues concerning renewable energy are in particular for new buildings, the design of new buildings, like solar passive design, but also the storage of thermal energy, the thermal mass of an object. In fact, the existence of Dynasty is a result from passive solar design of buildings that we started 35 years ago, the well-known European PASSIS projects. In the near future, the energy balancing becomes important at infrastructure level. The building will become a key element of the energy infrastructure. So let us summarize what analysis of performance data has to deal with. First of all, variability. The variability due to indoor environment, the occupants, outdoor environment, climate, and weather conditions. It's also to deal with errors due to the measurement, due to instruments, sensor positioning. It has to do with accuracy, in particular of the input signals that are going to be analyzed by a model. The pre-processing of raw experimental data is important. Space and time filtering as well. The uncertainty that is coming from the modeling itself, measured and not measured phenomena, has to be dealt with. Dynamic information is getting into the picture, and in particular the correlation of input signals. So What is it that Dynasty aims to do is to train a methodology, a common methodology for an analysis. Note that analysis methodology is not an instrument. You do not get just a value out of an apparatus. Analysis of data from time series means that data signals have a common time step. This is essential. Data is supposed to contain all relevant information, in particular the dynamic information, to describe a physical process. Relevant means that the applied methodology should support the expected result. I'll come back to that. Physical process is defined by physical parameters in which we are interested. Common methods that we today will consider are the steady state or the average method, but that can only assess the thermal resistance as a steady state value. The results should be considered as a rough indicator. Note that dynamics or the thermal capacitance cannot be estimated. Concerning dynamic methods, we will discuss during the upcoming 6 presentations thermal networks, LORD, that will be presented after my presentation by Paul Baker. And we will consider also statistical models, gray box models, and that it will be presented later in the webinars, for example, the CTSM. How to go from many observations to a desired value, a valuable result. The valuable result depends also who is going to use the result. The result might be a number, a data series, a graph, or even a range of colors. Some people do not like numbers and prefer colors instead. The applied methodology should deal with it. It's a link between many observations and the limited value of the output. How to start with a huge amount of data? Well, the first step is pre-processing. Pre-processing. If you get a huge amount of data, just plot it and try to understand what it exactly represents. Check for not regular signals. Apply the average method to get some feeling with the data. Basic statistical information can give more clarification and start trying to filter in space, and it means that you try to reduce similar sensor signals to one and or reduce interval of observations to, for example, hourly data. If you have minutely data, you can choose 10 or hourly data. But remember that with every filtering, you throw away information. So it is up to the user to decide up to what level he applies a filtering technique and what kind of data he or she is using. Well, let's start with the average method that is giving you a rough indication. The average method is straightforward, and we have expressed it here on this slide. It can be used easily, and it can be applied in different ways as well. In order to give insight in the available data, the whole data series can be divided in different periods to check for inconsistencies. Also, in the case of solar radiation, the impact can be considerable, as we will see later. The periods that you may select are including or excluding solar radiation, so you get a basic information about the data. Most people use the average method by applying an increasing length or by a moving average of 10, 20 observations depending on the interval and the available observations. So what you see is what you can expect from an increasing length. So as you also can see is that it is after observation 21 that it is already varying in something like 10–20%. So is this accurate enough? No, but we have information about where we can expect the final result. In this graph, we observe solar radiation on sensors. What you see it is the heat flux sensors, different heat flow sensors in a box, and the box is having a window, and the solar radiation is affecting importantly the signals from these type of sensors, depending on their position and its sensitivity. So it is very important to understand the data. So you should recognize most of the time it is the impact of solar radiation. So check the data for common behavior. However, your knowledge about the physical process is required. In general, temperature sensors as well as heat flow sensors will show in the plot different behavior when it is hit by solar radiation. So in this one day that you are seeing in this graph, the impact of solar radiation is on the west, east, ceiling, and floor. That it is important to understand that it is a signal from the sensor, and not of the whole surface that it is expected to represent. So the sun will hit the sensor, although it is already hitting the surface area before. So that is why these strange behaviors are to be interpreted. I have mentioned so far some expressions, and before continuing, let's make clear some definitions of a model, a method, and a tool. A model is a mathematical description of a physical system or process. By definition, it is a simplification of reality. A method, like CTSMR, that will be presented in one of the next webinars, consists of two major parts. First of all, it is having a mathematical model that is based on your knowledge of the physical system. And the second part is the estimation of the model parameters. And the trick is, one of the tricks is to use the least squares method to reduce the error between the measured signal and the simulated data. So it is in fact the application or a process of optimization and minimization. And a tool is a sophisticated software program which allows the user to apply a certain method in a user-friendly way. LORD is such an example, and it contains two methods, the output error method and the prediction error method. LORD will be presented by Paul Baker immediately following my presentation. Remember that the world is managed through models. The model is a simplification of reality, and it is made by you. You are responsible, and it is based on your interpretation of reality. You can wonder what colored sunglasses are you wearing, or what spirits did you use in order to define a certain observation in a mathematical way. In general, all the approaches have in common the need for data, so the quality of the data is important, and the data can come from one or more resources. A method that we have agreed upon to assess a desired result has to be chosen, and a set of tools, including statistical tests, are required to carry out the analysis leading to the desired result. What is the expected result? Who requires the result? What accuracy should the result presented with? So, and as you can see in this right bottom graph, some people really like colors. What we have found out more. I started my presentation by saying that the dynasty is a multidisciplinary grouping. During more than 25 years, it became clear that in particular building physicists and statisticians did not always have the same opinion and development aims. We concluded that building physicists solve a physical problem using mathematics, whereas statisticians solve mathematical problems. Physicists, they show more interest in lower frequency, while statisticians focus on higher frequencies. Also presenting results like for temperatures, for example. Physicists, they prefer 7.1, whereas a statistician will present 7.085 degrees Celsius. However, together as a team, they perform successful dynamic analysis. Looking a bit more in detail, we may note that a building physicist says, well, the model should describe the physical process, and he seeks physical parameters. He can cope with not measured phenomena and focuses on low frequency. His interest may start from static or steady state situations before entering the dynamics of the process. A statistician declares that the model should fit the data, and he seeks mathematical parameters. The residues should be white noise, and hence he's focusing on high frequency. His interest is from the beginning the dynamics of the process. So the conclusion of the dynasty network is that building physicists and statisticians are a good combination to deal with dynamic analysis for the energy performance assessment of buildings. Although it is not always easy. The identification of physical parameters of a system in the context of energy performance assessment of buildings is focusing on the assessment of thermal parameters. We state that it is the application of a mathematical model representing a physical system using measured data, in which the user plays an important role to assess physical parameters from a set of mathematical equations. So we have put there graphically the user in between the whole situation. A general representation may clarify a little bit. So if we have a lot of input available, we can put that in the system. We have an output, a desired output requested, and we have to deal with disturbances. That can be anything from errors to modeling assumptions, etc. It is applicable to different physical systems, for example, electrical systems, water flow systems, and of course, heat flow transfer systems. What you see is here is a very general representation of it, where the prediction error model is the basic. The output error method or model is a special case of prediction error method or model. The prediction error method minimizes for each step the error, whereas the output error method, as the abbreviation is already mentioned, minimizes the output after calculation the whole set of data. So summarizing, we have a set of differential equations and we apply a set of statistical rules and solve the best set of mathematical parameters by minimizing the error between model output and measured data. Essential is this minimization, and one of the easiest ways to do it is to apply the least squares method. It results in a residue that can be examined also graphically. I will show you in the next slide. The expression to calculate the minimization process is given on the bottom of this slide. What you see here is that measured and calculated data can be plotted against each other. Also, the residue itself, so the difference itself, can be plotted. I come back to that later. Let us move a little bit in the direction of the application of an analysis method. First, model simplification. Imagine a three-story building. And you can say it is defined by an envelope, a building envelope. That means it is exposed to external climatic conditions. And it has a volume, an internal environment where comfortable conditions for working or living are required by the minimum requirements of the member states. Through the envelope, the walls and windows, there is heat transfer. There is also ventilation losses because you need to have fresh air. The space is affected by gains, often variable by solar radiation through the windows, but also by appliances or the behavior of occupants. As it is shown here, it is quite complex, but a lot of data might be available. But it is better for the analysis to start from a much simpler representation and make the work more complex in the other way, in the other direction. So if we consider the envelope and the volume, then there are some issues to focus on. Keep in mind the process of heat transfer and the increased complexity that can be observed. Heat transfer by conduction only is given in the first figure. You may deal with distributed thermal mass in the envelope, but we excluded here the impact of convection and the impact of radiation. So we only deal with the transfer by conduction. This is the most simple way to start with. But in reality, often the situation is more complex, and the transfer of heat is by conduction, radiation, and convection. That is given in the second line, and that takes place in particular in walls where there is an air gap, or between window layers when there is an air gap, etc. And then the situation is where we are dealing with a volume and closed system. It's a space, and the construction gives also some not measured phenomena that occur, like infiltration, like corner effects, etc., etc. And we try also often to get the information from a wall where there is a door or a window placed. So we have to deal with not measured phenomena as well. That will be the most complex system that we have. So this 3-story building may become a one-zone object in its first simplification. It has to deal with different ambient temperatures, exist as well as different wall compositions, including yes or no windows. Corner effects may take place, as well as stratification in the space, in the volume. And of course, the impact of solar radiation through the windows. That might give a seasonal impact. In order to get their mathematical equation, one may apply the process of lumping or ignoring. However, the user should be aware of what is done, because you cannot model successfully if the data does not contain the relevant information. That is probably always the case when you are looking into corner effects, because there's hardly data from measured corners. In fact, here shown what the mathematical formula is representing. All heat transfer characteristics are in one parameter, which is the UA on the left in the formula. The impact of solar radiation is put in the GA, solar aperture. It's also one parameter. We are excluding corner effects, so the whole zone is becoming a sphere where you have an indoor temperature and you are dealing with one ambient temperature. So there are no corner effects, and all the not measured phenomena are neglected. This could, however, be your starting point for the analysis. There are several routes to get to your final destination. We will have 2 perspectives that will be discussed and applied using 2 approaches on benchmark data. That is in the next presentations all applied. We are looking into LORD. They are using lumped parameter models. And we are looking into CTSM in the R environment, and that is mathematical techniques on continuous time models. That will be in a week from now. To demonstrate how it works, we have selected some benchmark data that will be used. During the years, Dynasty has been keen on making high-quality data available for training of analysis method. These data will be studied by many participants in our workshops, summer schools, etc. 3 benchmark series are presented during the webinars and will be available for download from our website. So you can start training, self-training at home, and then if you have problems, you can come back to us in the question and answer session by the end of the month. Consider a stepwise approach. Use an environment that you are acquainted with. That can be MATLAB, Excel, or whatever it is. And mind the first steps as are mentioned in the beginning of my presentation. You can use MATLAB, Excel, and you can apply the average method. You can look to the data, you plot it, and you can recognize maybe errors, you can recognize maybe the impact of solar radiation, etc. Keep already in mind also the tool or the methodology that you like to apply. Sketch on a piece of paper how your model could be representing the physical process. All these kind of things are just as a starter. So start to understand the available data by plotting it. and apply the average method. And then you should think about how you go from measured data to model input data, as explained in the pre-processing part. How to go from many sensors like temperatures, indoor air temperatures, for example, to one input air temperature for your model. Understand the reduction of data. That means filtering in time or in space. Understand also model reduction, what I've just briefly represented. In particular, the physical consequences of simplification. And then we advise also that you should challenge yourself. Develop a skill, perform exercises in order to understand how mathematics are dealing with your problem, with your physical problem. And very important is also try to motivate your decision making. Why are you reporting a certain result? So summarizing, it means a stepwise increment of complexity. Here we put it again from data using the tools, plot the data, average method so you get a rough idea of what it represents. By regression techniques, introduce some dynamics, use the ARCs or ARMAX models, and maybe at the end you may decide to apply a gray box models. That is exactly what we are trying to do with our presentations. We start from the not too complex situations, and we will end up by the last webinars, the application of CTSM, the application of the gray box models. The resulting accuracy, I need to put the word out as well. The resulting accuracy of the analysis estimate depends on three types of errors. You should understand it. Experimental boundary conditions, the choice and the position of sensors. That is not always done by you, but by another person who is responsible for the experimental setup. The reduction of input signals, well, that is up to you. It depends on the setup, how many sensors are placed and where are they placed. There is also, of course, the accuracy depending on the measurement error, the sensors, instruments. Maybe we can go back to the calibration of sensors, missing observations. And then we come more or less to the error introduced by the analysis method. And that is more the problem of your model, of course, and the conversion of mathematical to physical parameters. And remember that we are interested in physical parameters, and that might be problematic. Another issue is the correlation between input signals, and that is often caused by solar radiation, because you can expect that if solar radiation is passing a window, also the indoor temperature will raise. After the analysis is performed, sometimes a time-demanding process, prediction error methods are consuming more power from than the output error method. You have an expected result, and then it is time for post-processing. I've listed here some essential points for doing so. This is more in detail in our summer school, but you can quickly go through it. Well, the result should fit to the data, and this is what you can find by examining the residuals. They should be small and white noise. It should be also a reliable result, which means that if you use different data of the same object, that the results should be the same. Internal validity, it's cross-validation. If the physical system did not change, assume that it is not changing. External validity, you may have results that are coming from literature, Dynamic stability, if you change, if you put a step on your input, then your model should fade away from the changes. And the identifiability. Model parameters are uniquely determined by the data. In that context, should remind us the conversion from mathematical into physical parameters. So again, more details on post-processing are presented in the physical summer school that will take place in June 2021. The examination of residual analysis is also tricky. You should be sure that your mathematics, your process is getting the lowest minimum of it. And in this graph, you can see that in some cases there are several minimum, but your system should be sure that it is really the minimum that can be found. Lord offers this possibility and might restart the minimization process from other starting points. One of the tricky things that are occurring, do not expect immediately that your mathematical process is giving the minimum. Study also the residual plot and recognize patterns. For example, the daily repetition of solar appearance, what you can see in this graph. Do not always expect white noise, since your model might be too limited. In this case, you may say, okay, the impact of solar radiation can be modeled, or I ignore it. And, maybe Paul will also mention that with Lord, you can put windows, day and night windows over it. So as I said before, as an exercise for you to start with, we have made available data, and to start with, we have made available simulated data. There are two cases, two benchmark cases. Case A is quite simple and should give you confidence because we have given the creation data. Case B, we kept this creation data secret and only noisy simulated data is given. You may decide to apply your own method, but Lord might be an option after you have decided and listened to the presentation of Paul Baker. So data has been made available on our website. Go to Dynasty Info, Data Analysis, and on the page of online training, you will find the link to download the data. People in general do not have much problems in estimating the thermal resistance. You see here the results from 12 participants from a long time ago. Most of them, they did not have any problem, and they are on the blue line, they are quite close. But more problematic is the thermal capacitance. These are the red dots. And I'm sure that also you will find problems in assessing the capacitance. We would be very interested if you give us your, by reply, your results from the first exercises. And you should see if you get in between the spread that are giving these 12 participants. Training makes sense, and that is what we like to emphasize. I'm getting now to the end of my presentation, but I'd like really to emphasize that training makes sense. Here one may see the impact of training before the exercise, and that is the group of people that were participating in one of our workshops. We have given training before, and then we have distributed the data to them. And you see that the results are more or less as we would like to see the result. It is different if you look to the situation where we have given first the data and then did the training. So before the summer schools in 2012 and 2013, we have distributed the same data, and we were wondering if it is really giving the same quality of results. Well, for us, the conclusion was clear. Well, we need to make training. We need to give some lectures in order how to deal with a proper analysis. And this is for us a very nice demonstration of that training makes sense. So the conclusion of Dynasty is one needs to develop a certain level of skill to perform well. You should improve the knowledge through training and competition. And you may decide to visit our next summer school in Almeria in June 2021. After 25 years, we as a grouping, we may say that training makes really sense. I thank you for your attention. I hope that this presentation has been informative, and if there are questions, we can see if there is some time left to answer these questions.